So, good evening, everyone. Welcome you all to this NPTEL course entitled as a Study Guide in Organic Retrosynthesis Problem Solving Approach. The course instructor for this course is Professor Samik Nanda and from IIT Kharagpur, and myself Anirban Maiti from IIT Bombay. So, I am one of the TA for this course. So this for this course we have this so the as the topic of our course is heterosynthesis, so we have discussed many times about this heterolytic cleavage of a CC bond, carbon carbon single bond, and and then we can get the donor syntone and acceptor syntone, and among them we have discussed about the synthetic equivalent with respect to donor syntones, also synthetic equivalent with respect to acceptor syntones. So this all we need in our retrosynthetic problem analysis. So that's why I gave this slide. So coming to our first problem for uh, today's tutorial. So this is the molecule. So this six-member molecule. Okay. So this is yeah. If you see this molecule, it is having one olefin like CC carbon carbon double bond and one carbonyl functionality. So how we can plan for a retrosynthesis for this molecule? So what we can think about for this retrosynthesis? Yeah, in if as it is six-member ring, so if you see six-member ring, then the first thing that will come into your mind that six-member ring could be made via 4+2 cycloaddition reaction or Diels-Sala reaction. So can we make this molecule via Diels-Sala reaction? Just think in your mind, can we make this molecule via Diels-Sala reaction or not? If yes, then how? Or if no, then why? So let's see whether we can make via Diels-Sala reaction or not. So if you see this molecule, okay, so Diels-Sala reaction we can get cyclohexene. Okay, so if we want to see whether it could be made by a Diels-Sala reaction, then just see the arrow push mechanism. So this can fall here, this can fall here, and this can fall here, right? Yeah. So now, so Diels-Sala reaction, if we want to think about, so what will be uh, the corresponding diene and dienophile? So this is simple 1,3-butadiene, 1,3-butadiene normal, 1,3-butadiene. This will be the diene, and the dienophile, if you see, that is a ketene. Okay, so here the dienophile is ketene. So this is the ketene, and here if you want to do Diels-Sala reaction to get this target molecule, then you need to do the Diels-Sala reaction between this ketene and this 1,3-butadiene. Now the problem is that ketene will not undergo Diels-Sala reaction. Okay, some so in the cycloaddition topic, I guess all of you know that Dils ketene will not undergo Dils 4+2 cycloaddition reaction, rather it will undergo 2+2 cycloaddition reaction. So it is a good substrate for 2+2 cycloaddition. So this 4+2 with ketene is very difficult. Okay, so, so as we see that this reaction with ketene will not work. So this we can't make via this this normal 2 plus 4 plus 2 cycle addition reaction, then what are the other possibilities? Okay, so how we can make this molecule? Again, we can think about Diels-Cellar reaction. Okay, but that time we need to use some different dienophile. Okay, instead of ketene we need to some different dienophile to get this molecule. Okay, so just think in your mind, so what are the other dienes that can serve as a ketene equivalent? Okay, just think, or you can write in your notebook. So some other like some ketene equivalent we can use as a dienophile in Diels-Cellar reaction. So for that, if we have this functional group in this cyclohexene, like nitro group instead of carbonyl group, if we have this nitro group, then we can carry out the Diels-Cellar reaction to get this molecule. Okay, so again similar fashion, so like this. So like retro 4 plus 2 we have to do, and we can get this dienophile. Okay, so now this dienophile, there is no problem to undergo Diels-Cellar reaction. So here the in the first example this Diels-Cellar reaction is very much difficult, so it will not happen, it is not going to happen. And but here it is very easy to undergo this Diels-Cellar reaction with this dienophile. Okay, so this is the correct pathway, and in this case we'll like this is the ketene equivalent. Okay, so this dienophile we can call at we can call it as ketene equivalent, because the nitro we can at the end we can convert to carbonyl group, and if so at this can serve as a ketene equivalent. Okay, so Diels-Cellar reaction, via Diels-Cellar reaction we can get this molecule, right? So what will be the forward synthesis then? So now we need to prepare this dienophile. Okay, so this dienophile we need to prepare. So how we can prepare this dienophile? So if you see this nitro, so alpha beta unsaturated nitro compound. So how we can prepare? Okay, so I will give one clue. You can think about, like instead of nitro, you can think about alpha beta unsaturated ketone or aldehyde. Okay, so that is a very easy reaction for like 10 plus 2 reaction. We read in 10 plus 2 like how to get this alpha beta unsaturated aldehyde or ketone. Okay, so how we can make this similar compound? Instead of aldehyde we are having nitro, right? So how we can make this thing? Can you please answer how we can make? So basically we can make via aldol reaction. Okay, aldol reaction. So here it is nitroaldol, as nitro group is present here, so we can call it as nitroaldol reaction. Okay, so nitroaldol reaction, so we if we disconnect this CC bond, CC double one, then so like this nitromethane and acetaldehyde. Okay, so this will give this nitroallyl product or your dienophile. Okay, so under treatment of DBU, so DBU will abstract this nitromethane acidic proton from nitromethane, and then it will undergo this allyl reaction with this aldehyde. Okay, so this will be, so by this we can get our dienophile, right? So now the dienophile we got. So what will be the next? So what will be the next is to carry out the Diel cellular reaction. Okay, so Diel cellular reaction will happen between this diene and dienophile. So basically, so if you see, this will be the Aropus mechanism. Okay, so this will give the six-member ring cyclohexene. Okay, with this nitro group. Simply, basically, if you hit this two starting materials, both 1,3-butadiene and this dienophile, you will get easily, you will get this product cyclohexene. And then if you see our final compound, we are having this carbonyl group here. Okay, carbonyl group, instead of nitro we are having this CO carbonyl group. Okay, at this carbon. So how we can convert this nitro to carbonyl group? So earlier classes also we have discussed how we can convert this nitro to aldehyde or ketone. So I guess you can remember that we can do via NAP reaction. Okay, so NAP reaction is the uh, major reaction to convert this nitro to aldehyde. Okay, so there are many conditions to carry out this NAP reaction. So and some reductive methods are there, like using TiCl3 in water. We can easily convert this nitro to carbonyl. Okay, and this reagent is actually utilized by Professor McMurray. As you know, McMurray coupling reaction between two aldehydes or two, basically two carbonyl compounds. If you want to couple via McMurray coupling, then you have to use TiCl3. Okay, so these are single electron donor reagents. Okay, so McMurray coupling, and the Professor McMurray, he developed this NAP reaction via this TiCl3. So this is a reductive method to get this, to carry out this conversion. Okay, so you can easily get this your desired cyclohexene cyclohexenone. Okay, very simple, straightforward reaction. Now coming to this example. Okay, so this example, if you see this molecule, what are the functional groups we are having and how we can think about the disconnection approach. Okay, so think in your mind, or you can also write in your notebook, so how we can think about the disconnection approach. So just before that, you just think how many like what are the functional groups are present in this molecule, and then you can easily get an idea how we can break the CC bond. Okay, so if you see this molecule, it is having one carbonyl group and another hydroxy group. Okay, and if you see the position of that carbonyl group and hydroxy group, that are alpha. Okay, like alpha hydroxy ketone. Okay, so how we can plan, or what disconnection we can do? I am giving a clue, like this CC bond disconnection approach we can think. Okay, So this CC1 disconnection approach we can think. Then what will be your synthons? Okay, I think before this CC1 disconnection, we can do some functional group interconversion or FGI. Then we can think about this CC1 disconnection. Okay, so if we do some FGI, functional group interconversion, from this alkyne, okay, so this is the terminal alkyne. So this alkyne we can convert to carbonyl compound. There are many methods. In 10 plus 2 also we have read about this alkyne to carbonyl conversion. That is very pretty easy, straightforward. Then we can think about this CC1 disconnection. Okay, now we can easily write down the synthons for this CC1 disconnection approach. So just write in your notebook what will be the synthons for the CC1 disconnection. Then I'll show you. So this is also straightforward. Just you can think about this acetylene from this side as a nucleophile and this side as a electrophile. Okay, so what will be the synthons? Synthons will be like this this carbon acetylide anion. Okay, acetylide anion C minus. So this will be the donor synthon and acceptor synthon will be the OH. So this will be the acceptor synthon. And what will be the corresponding synthetic equivalence? Okay, the synthetic equivalence, this will be the acetylide anion synthetic equivalence. So acetylene will be the synthetic equivalence for this acetylide ion, and this alcohol part. So for this part, synthetic equivalent will be the corresponding ketone, or that is acetone. Okay. So any doubt for this retrosynthetic disconnection approach? So if you don't have any doubt in this retrosynthetic disconnection approach, I'll go to the forward synthesis. Let's see how we can synthesize this molecule in forward direction. Okay. So first we have this acetylene. So we need to make the reagent. Okay. So this is the starting material. Now we need to convert this to reagent. So how we can make? Basically, we need to generate that acetylide anion. Okay, acetylide anion. So how we can generate acetylide anion from acetylene? Can you tell me? So basically, we need to treat this acetylene with any base. Okay, what type of base we can use to get acetylide anion? So we can treat with NBTEL lithium. That time we will get lithium acetylide ion pair, or we can treat with sodamide in liquid ammonia to get that C minus Na plus. So the counter cation will be the sodium plus. Okay, so we got this acetylide anion. Now we need, so this is the donor syntone for retrosynthesis, but now it is the nucleophile. Okay, so now this nucleophile, so of course you need some electrophile to get your product. So according to your retrosynthetic analysis, the corresponding electrophile is your acetone. Okay, so if you treat it with acetone, you will easily get this addition product, 1 2 addition product. So acetone. So basically, there is only one possibility to do 1 2 addition. There is no other possibility for 1 4 addition product. So only 1 2 addition product you will get, and it's you got this tertiary alcohol. So this alcohol, if you see, so this is tertiary alcohol. Okay. So now what will be the next? What is the next step? Basically, if you remember correctly, you need to get some carbonyl group here. Okay. So we talk about when we see when we saw the molecule, no, that time we discussed that it is alpha hydroxy ketone. Okay, so basically we need some ketone at alpha position, alpha to this hydroxy group. So we need to convert this compound to alpha hydroxy ketone. So how we can do that is very straightforward reaction. You can easily do. Just think about some reagents in your mind. Otherwise, I can give you some clue to carry out this conversion. So there is some reaction, name reaction known as oxymercuration demercuration in alkyne. Basically, silver chemistry, not silver, mercury Hg2 plus Hg silver acetate you have to use, and then sodium borohydride. So you'll get this oxymercuration demercuration product. First oxymercuration onto this alkyne, followed by demarcation by using sodium borohydride. So you'll get this hydrolysis product. So hydrolysis, basically hydrolysis of alkyne. Okay, and you will get this alpha hydroxy ketone. So this is our target molecule, right? And you can see how easily we do synthesis of this target molecule. So I guess you don't have any doubt, or if you have any doubt, just ask me for this particular problem. Okay. So then we can move problem here. So if you see this carbonyl, this compound, it is having dicarbonyl compound. Okay. So this is aldehyde, and this is carbonyl. Okay. Now how we can plan the retrosynthesis? Okay. So now if we think this molecule, how we can plan, or how we can imagine in our mind, or how you can visualize this molecule. Okay, So this molecule and this molecule are same basically. Okay, so both are same molecule. Okay, now you can easily visualize how this molecule we can uh, like how CC disconnection approach we can think in this molecule. Okay, so now we can think. So this is the carbonyl compound, this is the alpha carbon, and this is the beta carbon. Okay, so this alpha beta to this carbonyl compound, so we can easily plan the red CC bond disconnection for this is this CC bond. Okay, so we can think this carbon can be a positive and this carbon can be a negative charge. So basically, alpha beta unsaturated compound we can think about, and for this part we can think about Ompulang chemistry. Okay, so this alpha beta unsaturated compound. So this is the synthetic equivalent for acceptor syntone, right? And what will be the synthetic equivalent for this donor syntone? So same nitromethane already we discussed in last slide, right? So very interesting example. Yeah. So in forward synthesis, so this is the nitromethane we have to take. So now, so nitromethane we are abstracting proton, right? So we will treat this nitromethane with base, and that base will abstract proton. So for this type of reaction we should know the basicity, the pK values for the corresponding acids, and pK value for the corresponding acids of corresponding conjugate acid of bases also. Okay, so this pK value we you should know, otherwise you don't know which base you will use in your reaction. Okay, so this pK value for this nitromethane is around 10. Okay, if it is nitroethane, so for nitromethane it is 10. If it is nitroethane, the pK value is 8.5. So basically you can, so the pK value for nitroethane is 8.5. So you can think the decrease of pK value for nitroethane. So that is quite obvious, because this extra alkyl group methyl have plus I effect, and due to this plus I effect, so the acidity of this carbon will the proton of at this carbon will get decreased. Okay, so nitroethane pK value is 8.5, so nitromethane pK value is 10. So for to abstract the proton from nitromethane, uh, you have to use the base which is having pK value more than this base. Okay, pK value of base mean we are thinking the pK value of their conjugate acids. Okay, so in general we will say ki pK value of base. Okay, but that does not make any sense. So pK value of base mean we are telling about the pK value of the corresponding conjugate acids. Okay, so pK value of nitromethane is 10. So we have to use the base which is having the pK value more than 10. Okay, so we can use sodium methoxide. Okay, so that methoxide or ethoxide, that pK value of corresponding conjugate acid is almost 15 or 16, right? So we can use, so this base is sufficient to abstract this proton from nitromethane. Okay, so this nitromethane, and we take sodium methoxide in methanol, we can easily get, yeah, we can easily abstract the proton from here. So we can generate the carboanion. Okay, now if we treat this carboanion with this alpha beta unsaturated compound, so this carboanion will attack to the beta carbon of this unsaturated compound, right? So beta carbon is more electropositive, so we will get the corresponding product, right? So you get the 1,4 addition product or Michael addition product. So this is the Michael addition product. Michael, yeah, Michael addition product. or on for additional product. Now the next step is basically you have to do the NAF reaction. Okay, NAF reaction already we have told about, do we have discussed. If we treat with titanium trichloride in water, we'll get the corresponding nitro 2 and this aldehyde. Okay, so this was our target in retrosynthetic analysis in last slide. So now in this slide we see how we can carry out the reactions to get this TGR product. Okay, so I guess you have get an idea about NAF reactions or Ampulang chemistry. Okay, so the next slide. So and this compound is equivalent to this compound. Okay, so in next slide we'll see the retrosynthetic analysis for this compound. Okay, now if we plan the retrosynthetic analysis for this compound, so this is having, so this is yeah, this is having this alpha beta unsaturated carbonyl compound as well as gamma methoxy. Okay, so this is the alpha, this is the beta carbon, and this is the gamma carbon. So where are the substituents? So in at gamma carbon we have this O methoxy, and alpha beta is having double bond unsaturation and this carbonyl compound. Okay, so we'll plan the retrosynthetic analysis or forward synthesis from this alpha beta unsaturated cyclohexenone. Okay, so this is basically cyclohexenone. So how we can plan? Yeah, we will see in forward synthesis. Yeah, just a minute. Yeah, so from for forward synthesis, so we are planning the retrosynthesis for this compound, right? And the target material already we gave here. So this is cyclohexenone. So in forward synthesis, so we'll start from the cyclohexenone. So cyclohexenone we have taken. Now the next is we can add the lithiated pieces. So this 1,3 diethane derivative. Okay, so basically ampulang chemistry. Okay, so this is basically uh, acetaldehyde, right? So acetaldehyde, so how we can generate this acetal, the corresponding lithiated species of this acetaldehyde? So we can generate from uh, this 1,3 diethane species, and already we know the pK value of this proton is 31. Already we have I have shown you. Okay, so pK value is 31 now. So we have to take a stronger base, so which is having pK value more than 31. Okay, so we can think about this n-butyl lithium which is having pK 50. Okay, now I guess you have heard about secondary butyl lithium. Okay, secondary butyl lithium, I will show the pK value for secondary butyl lithium, also tertiary butyl lithium. Okay, so oh, which one will be the more stronger base? Okay, so you can think in your mind. So in between in butyl lithium, secondary butyl lithium, and tertiary butyl lithium, which one will be the most stronger base? Can you guess? Okay, no problem. The pK value of n butyl lithium is 50. I'll mention the pK value of secondary butyl lithium, that is 51. Okay, and tertiary butyl lithium, that is 53. 53, the corresponding pK value of secondary butyl lithium and tertiary butyl lithium. So by seeing this pK value, you can clearly think that tertiary butyl lithium is more strong base than secondary butyl lithium than n butyl lithium. Okay, now here n butyl lithium is okay, because to handle secondary butyl lithium and tertiary butyl lithium is quite challenging. Okay, those are more stronger base, so in presence of moisture it can create explosive kind of things. Okay, so first we can generate this lithiated species from this 1,3 diethane by treating with this with n-butyl lithium, right? And we can get this lithiated pieces. Now this lithiated pieces basically this this C minus, right? So this C minus will attack now. Now if you see, it is having two electrophilic centers. So this cyclohexenone is having two electrophilic centers, right? So first one is this 1 2, and second one is this 1 2 3 4 4. So this center as well as this beta carbon, okay, both are electrophilic center. So now you are adding this nucleophile into this molecule. So what will happen? Two possibilities are there. It can attack at here, or it can attack at here. Okay, so now if you use simply this lithiated pieces, so basically this 1 2 addition will happen, so this reaction will not happen. And when this reaction will happen, if you add HMPA, hexamethyl phosphoramide, okay, HMPA is a highly polar aprotic solvent. So I will tell you the role of HMPA in next slide. Okay, so when 1,4 addition will happen, so 1,4 addition will happen when you will use HMPA, but without HMPA, normal 1 2 addition reaction will happen. Okay, so first basically in this case you will get this 1 2 addition, right? So this is the case, 1 2 addition you will get. Now the next thing is that you have to do uh, yeah, you have to do the deprotection of this uh, 1,3 diethane. Okay, so how you can do? You can easily do by using this silver chloride, mercuric chloride, right? HgCl2 in water and methanol. So what will happen? You will get this corresponding carbonyl group here. Okay, so this group will deprotect and you will get the corresponding ketone. Okay, so you'll get ketone. Now this interesting thing is that you are using methanol in your reaction, and you are having the allylic alcohol. Okay, so this is the allylic alcohol. So what will happen? So Hg2 plus is there in your reaction medium. So this Hg2 plus will bind with this alcohol, allylic alcohol, and also this carbonyl ketone. Okay, so it will bind, so and it will make, so this is the 3-degree alcohol, so it can easily break this CO bond. Okay, so basically what will happen, the methanolysis of tertiary allylic alcohol. Okay, methanolysis of tertiary allylic alcohol, so basically this methanol will attack to this olefin in allylic position, to this olefin in vinylic position, and this CC double bond will migrate here, and this OH group C oxygen bond will disconnect and this alcohol will remove. So what you will get basically, so basically you will get this OMe at this center and double bond at this in between this CC. Okay, so basically you will get the product. So this is very interesting. So if you have this type of scenario in your molecule where you are having this tertiary allylic alcohol, also this alpha hydroxyketone, so in this condition, easily you can do the methanolysis. Okay, so this is our target molecule. So you can see how we can synthesize this molecule from this cyclohexenone. Okay, Now in next slide I will explain the role of this HMPA. Yeah, the role of HMPA. And so what is the yeah, what is the role behind 1 for addition when you use HMPA? Okay, so I will see this 1 2 versus 1 for addition role of HMPA. So basically this 1,3 diethane compound, so which is having pK 31, and if you want to deprotonate this CH, so you have to use this NPTEL lithium which is having pK of 50. Now, after having this lithiated pieces, basically this is C minus Li plus. Okay, C minus Li plus. So this is the compound. Okay, so C Li bond. So this is ionic. Okay, not covalent bond. Sometimes many people used to write this C covalent bond between C and lithium. So that is wrong actually. So you can better to write this C minus and Li plus because this is ionic. Now, when you are having this lithiated pieces, okay, lithiated carboanion. So, and if you treat this compound with this methyl vinyl ketone, so this is methyl and vinyl ketone. Okay, so methyl vinyl ketone is having two electrophilic center. This carbon and this carbon. Okay, now if you add this methyl vinyl ketone onto this compound, first in this first step, 1 2 addition will happen. Okay, now if you use interestingly, if you use HMPA, what is happening, the reactivity is changing now. So now in this condition it will add to the beta carbon. Okay, so basically 1 for addition. So very interesting. Okay, so in first case without using HMPA, we are getting this 1 2 addition product. So the secondary tertiary alcohol, and when you are adding HMPA, you are getting this 1 for addition. So, what is the chemistry behind this HMPA? HMPA is nothing but it is a hexamethyl phosphoramide. Okay, so this methyl, this P double one O, NME2, NME2, NME2. So this is sp3. Okay, this phosphorus center is if you want to know the hybridization, so this is the sp3 hybridized. Okay, so the what is HMPA? So HMPA is a highly polar, so it is polar solvent. It used to use as a solvent, and it is a highly polar, also it is aprotic solvent. Okay, so this is the character of HMPA. Now what is the role of this HMPA for this one for addition? So basically what will happen, so if you see this C minus and Li plus, so this is an so this is the corresponding carbanion, and this lithium plus is the corresponding counter cation, okay, of this anion. So if you don't separate this cation and anion, then normally this 1 2 addition will happen. Now if you separate this carbanion and lithium plus, this plus and minus, this cation and anion, if you separate, okay, then what will happen, this carbanion will acts as a, so the nucleophilicity of this carbanion will enhance, okay, increase. So that time it will undergo 1 for addition. Okay, so how you can separate this C minus and Li plus? So there are mm, many solvents or many coordinating agents, so like HMPA. How what will happen, so this HMPA, so this is the HMPA, so it will coordinate lithium plus basically. So by coordinating this lithium plus, it is making this carbanion free. Okay, so that's why the nucleophilicity of carbanion become more. Okay, so it can easily as a adds at the beta carbon. Okay, so this is the role of HMPA in 1 for addition reaction for this 1 3 diethane case. Okay, so I guess you have get idea what is the role of HMPA. Also, there are many reagents like DMPU. Okay, DM. So similar kind of compounds, so DMPU. So sometimes people use DMPU. Also, sometimes people use TM tetramethyl ethylene diamine. So the role is same. Okay, so compounds are different or reagents are different, but the role behind this is same. Okay, so both DMPU, TMEDA or HMPA, it will basically solvates the cation. Okay, lithium plus, and by solvating this lithium plus, it is making the nucleophile stronger. Okay, so that is the main scene for this type of case. Yeah. Now, so I guess you get an good idea of, about using this HMPA in on for addition chemistry. So this is the another molecule. So how we can think about the retrosynthesis, think about the retrosynthesis for this molecule. Okay, so if you see, so first you just check what are the functional groups present in this molecule, then think how we can synthesize those functional groups, or how we can convert some particular functional groups to some desired functional groups. Okay, just think what are the functional groups and at which position these are present. Okay, so first it is a six member ring, and if you are having one carbonyl group, you are having one methoxy group at alpha position to this carbonyl, and you are having one double bond, carbon carbon double bond, that is alpha beta position, at alpha beta position compared to this carbonyl group. Okay, so how we can think about some retrosynthetic disconnection approach. So this can we make by a digital reaction, as I discussed the first problem, that was cyclohexene type of system. Here also cyclohexene type of system is there, but so can we also make this by a digital reaction? Just think whether we can make by a digital reaction or not, and if not, then why? And for Diels-Siller reaction, what will be the, if you think for Diels-Siller reaction, are the what are what are the diene and dienophile we need for this particular substrate? If you got the diene and dienophile, you can easily comment on whether Diels-Siller reaction will work or not. Okay, so if you see cyclohexene type of system, first you can think Diels-Siller reaction, but you need to think about that forward reaction will also happen or not, like 4 plus 2 will also happen or not. Okay, so let's see if Diels-Siller reaction is we are thinking, then what will be the diene and dienophile. So this and this. Okay, so I guess the diene will be, oh my god, this type of diene. Okay, so this is a diene, and what will be the dienophile? Oh, sorry, there is dimethyl substitute here. And what will be dienophile? Dienophile will be the simple ethylene. Okay, so so now you just comment on whether this Diels-Siller reaction between this diene and dienophile will happen or not. So this Diels-Siller reaction is very difficult to happen, undergo this, to get this product. Why it is so? Because as in our first example also I have discussed about some ketene chemistry and Diels-Siller reaction using ketene chemistry. So here also this is ketene. Okay, ketene type of system. So as in our first example, we have seen that ketene will not undergo Diels-Siller reaction. Rather, it will prefer 2 plus 2 cycle addition reaction. So what will happen basically here, instead of getting this 4 plus 2 cycle addition reaction, we will get this 2 plus 2 cycle addition product. Okay, so you'll get this cyclobutane kind of thing. Okay, cyclobutane. So here you will not get any dissimilar product or 4 plus 2 cycle addition product. Then what will be the other possibilities? So what will be the other possibilities? Just tell me. So dissimilar reaction will not happen. So that is cross. No dissimilar. So if you see this functional groups present in this molecule is alpha beta unsaturated carbonyl compound. Okay. So one of the easiest way to make this alpha beta unsaturated ketone is aldol reaction. Okay. So aldol reaction is very famous reaction to get alpha beta unsaturated ketone. So now you can think. So what will be the like for aldol? So we can think about some aldol reaction to get this molecule. Then what will be the corresponding electron for this molecule? Okay, via aldol reaction. Just write in your notebook. So what will be the aldol? So what will be the electrons via aldol disconnection, aldol reaction? So basically this CC bond disconnection we have to think. So basically here aldehyde. Okay. So this aldehyde and this above side chain will remain same. So this will be the your electron. So now how we can make this molecule? Okay, so this the first retrosynthesis is done. Now for this molecule, how we can think about the retrosynthetic disconnection approach? So what will be the other disconnection approach? Just think and draw in your notebook again, and I'll show you. Okay, so we can think about this CC1 disconnection approach, where this will act as a donor syntron this part, and this part will act as a acceptor syntron. Okay, so for this acceptor syntron, this will be the synthetic equivalent, that is the alpha beta unsaturated carbonyl compound, and for donor syntron, this is the normal propanaldehyde. Okay, so this will be the uh, donor syntron, like synthetic equivalent for donor syntron. Okay, so this is our synthetic plan. Now, what will be your forward synthesis then? So the forward synthesis, if you see, so first we are having this yeah, propanaldehyde. one, two, three, four. Sorry, isobutanaldehyde, and this pyrrolidine. So this is the pyrrolidine base. So what it will form? So if we react this aldehyde and this pyrrolidine, what it will form? Just write down the structure of this of this corresponding product. So basically, first imine will form, right? So this aldehyde and this amine. So first this. So this is the aldehyde carbon, and this will make iminium ion, right? So now this iminium ion. So now this is having some acidic proton. So like let's say this hydrogen. So this hydrogen will underfall here. CH bond will break, and this will get neutral. Okay, this bond will get neutral. Like this one electron will fall to nitrogen, and nitrogen become neutral. So it will produce this enamine. Okay, so it will give this enamine. So pyridine and this isobutanaldehyde will give this enamine. Okay, so now what is the role of this enamine? So basically, enamines are in nucleophilic in nature. Okay, so it is now nucleophile. So you need some electrophile to react to it. Okay, so what will be the electrophile according to your retrosynthesis? Okay, so you generated the corresponding enamine from this isobutanaldehyde, so that will act as a nucleophile. And what will be the electrophile? Can you comment on that? So it is already written in this slide. Just tell me what will be the corresponding electrophile. So the electrophile is basically this alpha beta unsaturated carbonyl compound. Okay. So this enamine we got, now we need to convert, we need to add this enamine to this electrophile where the electrophilic center is this beta carbon. Okay, so alpha beta unsaturated ketone. So the beta carbon is most electrophilic. So this enamine will act as a nucleophile. So basically this nitrogen lone pair will fall like here, and this double bond will react via this carbon to this beta carbon. Okay, so this beta carbon is now electrophile, and you will get this corresponding CC bond formation product. Okay, this CC bond formation product. This now what will be your next conversion? Okay, so basically we got this product. Now in forward synthesis, what next we have to do? So we need to do this aldol reaction in forward direction. Aldol reaction we need to do, so some conditions, right, some bases we need to use. Some bases we need to use to get our like sodium hydroxide, like base we need to use to carry out this aldol reaction. Okay, so aldol reaction first, this alpha acidic proton, it will abstract, base will abstract this proton, and it will generate enolate. Then enolate will attack to this aldehyde, and you will get first beta hydroxy ketone, then this elimination of beta hydroxy group to get this alpha beta unsaturated ketone. Okay, pretty simple or straightforward. I guess no doubt. If you don't have any doubt, then we can move to the next slide. Okay, so we'll see the next problem. The next problem is this molecule. So this is now aromatic compound having amine here, here aromatic amine, here aliphatic amine. So two types of amines are there, or amines are present in this molecule. So what will be the retrosynthetic plan for this molecule? So let's see. So we can think about some FGI, functional group interconversion, like this nitro from nitro we can get this amine, right? So this FGI we need to do. Then so okay, now it is pretty easy. So now what will be the next? Okay, what will be the next? I'll give clue the what will be the next CC1 disconnection approach. Okay, now no FGI, just some CC1 disconnection approach. With CC1 we can disconnect and we can get the product. We can get the electrons. Okay, like for next retrosynthetic disconnection approach, what will be the CC1 disconnection? So if you see this next to nitro, this carbon, it is having these two methyl. So both are symmetrical, and this is a benzyl. Okay, now we can think about either this CC1 disconnection or this CC1 disconnection. Okay, this CC and this CC1 disconnection will give you the same result. So just better to say this CC1 or this CC1 we can blend. Okay, now which CC1 will be the more appropriate? Okay, which CC1 disconnection will be the more logical? Okay, just think until answer, or you can write in the comment section. Like suppose this 1 2 disconnection will be the more easy, or 1 3 disconnection approach will be the more approach, like more logical. Think if we think this CC1 disconnection, so definitely alpha to nitro is nucleophile. Okay, alpha to nitro we can easily create, like we can easily generate that carbon ion. Okay, now so this either carbon number 2 or carbon number 3 should have some electrophilic uh, character. Okay, so now which one will be the better electrophile? This is the benzyl. If you see, this is the benzyl electrophile, and this is the methyl electrophile. Okay, so which one will be the most good electrophile? So just answer is already ready. You can easily tell. Always benzyl electrophiles are like benzyl bromide or benzyl iodide, benzyl chloride. Those are benzyl carbocations. So those will keep benzyl carbocation. Those will undergo through benzyl carbocation, right? So benzyl carbocations are more stable. So that will be the most like good electrophiles. Okay, so better to do this CC1 disconnection approach. Okay, and you see what will be your reagents. Okay, so this isopropyl nitro isopropyl group, also as well as this 4 nitro benzyl bromide or paranitro benzyl bromide. So this will be your electrophile and this is your nucleophile. Basically you can easily generate carbanion here and it will undergo SN2 to give this product. Okay, any doubt? So then, okay, if no doubt, then we just move to see the forward synthesis. So fast forward synthesis. So this nitroisopropyl group we are having, and we are treating with this sodium ethoxide. Okay, sodium ethoxide basically Na plus OIT minus. So it is an base. Okay, the pK value is around 15 to 16. So basically, it will abstract some acidic proton. So acidic proton is this acidic proton. Okay, so it will abstract this acidic proton and it will generate the corresponding carbon ion. Okay, so now this nucleophile is ready. And what is your electrophile? Electrophile is like this. Okay, benzyl bromide, paranitro-benzyl bromide. So you will get this product, CC1 formation product. So now what is the next reaction you have to do to complete your target molecule? If you remember correctly, then you can easily answer. What will be the, like if you remember correctly the target molecule, then you can easily do the next conversion. Like what we have to do from nitro compound to what we have to do to get our target molecule. Okay, if you don't remember, I will show our target molecule. So this is our target molecule. So in forward direction up to this we have reached, right? So this we have reached now. So nitro to amine, that reduction we have to do. So what are the conditions? So H to ranny nickel, that will give this, yeah, nitro to amine reduction product. Okay, so this is easy. No ways. So this is a straightforward reaction to get your product. Okay. So if you have any doubt in this slide, just ask me. Otherwise, I'll move to the next retrosynthesis problem. Okay, if no doubt, then let's see the what is our next problem. So again, this amine compound we are having, and it is also having this aliphatic amine both side, left and right hand side. So what will be the first retrosynthetic plan for to get this molecule? Just think and tell me the answer, or write down in your notebook. So in similar way, we can get like via this. So we can think about this right hand side some functional group interconversion. Okay, and we get this alpha beta unsaturated nitro group. Okay, now this we are having this alpha beta unsaturated nitro group. In our second problem also, we we were having this alpha beta unsaturated nitro type of systems. Okay, and we also planned the disconnection for that compound. Here also the same alpha beta unsaturated nitro compound. So what will be the next retrosynthetic disconnection approach? Straightforward, just think logically and you will get the answer. So just tell me what will be the next CC1 disconnection approach for this molecule. Okay. Okay, so next CC1 disconnection approach will be this via allole reaction. Okay, so allole reaction we have already discussed that to get alpha beta unsaturated carbonyl, basically aldehyde or ketone, so that time we can carry out alpha allole reaction. But here the difference is we are having instead of having alpha beta unsaturated carbonyl groups, we are having this nitro group. Okay, no problem. Nitro groups also is electron withdrawing in nature, so similar type of reaction will undergo. So basically allole nitro allole reaction. Okay, so here we will call it as nitro allole reaction. So between this nitromethane and this aldehyde. So base will abstract proton from this nitromethane, and then it will add to this aldehyde, and you will get first beta hydroxy nitro compound, then elimination of that beta hydroxy group to get this product, right? So now nitromethane is okay, now commercially available. So now we have to think about this compound for retrosynthetic disconnection approach. Okay, so now what we can do for this compound, like what will be the retrosynthetic disconnection approaches? So the next will be the right left hand side. Okay, so this left hand side some FGI. Okay, so this we can get from the cyanide. Okay, cyanide, if we do reduction, we will get CH2NH2, right? So pretty simple. So we got this compound. Okay, and this we can get via this CC1 disconnection approach, where we this side part. So this side part we are thinking as a acceptor syntone, and this side part is as a donor syntone. Okay, so donor syntone is pretty much easy, isobutanaldehyde, and acceptor syntone will be this acrylonitrile. Okay, so any doubt in this retrosynthetic disconnection approach? Okay, then we'll see the forward synthesis. So forward synthesis, we need to do first this one for addition reaction. So we need to, so we are having this electrophile. So this is the electrophile, and this will be the nucleophile. So first we need to generate the nucleophile from this reagent. So base we are having, so we can have this proton, we can abstract this proton, and we can generate the corresponding anion. Okay, like alpha anion to aldehyde, and that can add to this acrylonitrile or alpha beta unsaturated cyanide compound, and this will give to your this addition product. Okay, on for addition product. So now the next reagents is drawn here. So what will be the next product? Nitromethane and triethylamine is the base. Okay, nitromethane is the reagent. So what will be the next product? Pretty easy. So nitromethane is base. It will abstract proton. Where is the acidic proton? Just see. Acidic proton alpha to aldehyde is not there. Alpha to cyano is not that much acidic, but nitromethane, this methane, so this pK value is around 9. Okay, so this is more acidic compared to the other this acidic proton. Okay, so basically this is the pK value. So this nitromethane will take that acidic proton and it will add. Okay, it adds to this aldehyde. Okay, and it will generate fast. What product you will get first? So first you will get some beta hydroxy nitro derivative, and then that will undergo elimination reaction. Okay, that beta hydroxy group with respect to this nitro group will undergo an elimination reaction to give this first this beta hydroxy nitro compound, and then elimination will happen. Elimination will happen in presence of, you treat this molecule with some dehydrating agent. Okay, now here we use P2O5, that is phosphorus pentoxide, and this is very much dehydrating agent. Okay, so this is commonly used as a dehydrating agent. So dehydration will happen. Okay, and you will get this product. Now what is the next? Yeah, here one mistake is there in this. So from this structure to this structure, I have also reduced this cyanide to CH2NH2. Okay, so first you have to use this reagent to get this beta hydroxy product. Then second step you need to use some reducing agent like H2. Okay, H2 palladium carbon, H2 palladium in charcoal. So you'll get this reduced product as well. Anyway, so that is the mistake. So I have corrected now. So the next is, so with treatment with beta P2O5 dehydrating agent, you will get this product. So now the reagent is shown here, H2 in ranitidine. So what is the source? What is the utility of this H2 in ranitidine? That is basically another reducing agent. So it will reduce your system. So what type of functional groups are present in this system to get reduced. Okay, first is nitro group that can undergo reduction, as well as this olefin. Okay, so that can also undergo reduction. So basically, you'll get this product. And if you remember correctly, so this is our target molecule. Okay. Okay, if you have any doubt in this slide, you can ask me. Okay, so then we'll move to the next problem. Yeah, this is the problem from tropinone. Yeah, this tropinone, yeah, it is first synthesized in 1917 by Robinson. This is the paper, Journal of Chemical Society. In this paper, he has published this molecule, the synthesis of this molecule. So first, if you draw this molecule like this, okay, this if you redraw this molecule like this, then you can easily visualize the next retrosynthetic disconnection approach. Okay, so now can you draw the retrosynthetic CC bond or CN bond or any other disconnection approach? Just draw in your notebook. Then I'll show you. So this tropinone we have drawn like this, like so. Now this is the nitro. Sorry, tertiary amine we are having. Also having this carbonyl group. Now this CN bond are beta position. Okay, this is the alpha carbon. It is a beta carbon with respect to this carbonyl group. Okay, bottom side also same alpha and beta with respect to this carbonyl compound. Now what CC or CN bond disconnection we can think? Already I have given clue that CN bond disconnection we can do. Like CN bond disconnection, if we do, what will be the product? So basically this CN bond and this CN bond disconnection approach, and we can think about some 1,4 addition product, because this amine is always nucleophile, then this alpha beta unsaturated ketones are electrophile. Okay, so we got these are synthon synthetic equivalent, and from then we got the synthetic equivalents. Okay, so we got this. So now what will be the forward synthesis? Okay, yeah. The next is we need to do the retrosynthetic disconnection approach for this as well. Okay, so this is alpha beta unsaturated ketone. Many times I have told what we can do to get this alpha beta unsaturated ketone. We can do, yeah, just think what we can do to get this alpha beta unsaturated ketone compound. We can do some known chemistry like aldol reaction, that is already told you to get this CC bond double bond product. But here we will do some other reaction, similar type of reaction, but the name is different. Okay, because the substrate is different. So here we can take this dialdehyde and this keto dicarboxylic acid. Okay, beta keto dicarboxylic acid, and we can do some same condensation reaction. Only we have to do allole type condensation, but not the allele condensation. Okay, so we'll get our desired alpha beta unsaturated ketone compound. Okay. So now in forward synthesis, so we'll start with this. So basically, if we take these two starting materials, this dialdehyde, malonaldehyde, as well as this beta keto dicarboxylic acid, so what will be our next? Okay, so product. So basically, you will get this product, this condensation product. Okay, between this aldehyde and this carbon, alpha carbon. So similar way, the next step will give this condensation product, and you will get this. So the next is the one for addition with methylamine. Okay, and you will get this product. Okay, now here I have written the CO2 elimination will take place. So what will be your product? Just write down the product structure. Then I will show you. So the product will be the elimination product, this CO2 elimination product at beta carbon, sorry alpha carbon. To get this product that is known as tropinone. Okay, and it was synthesized by Robinson in 1917, almost 8 years back. Okay, so now I will show the mechanism of this step. Okay, so there is one name reaction to carry out this conversion, that is Doebner condensation reaction. Okay, Doebner condensation reaction. So what is this Doebner condensation? So first pyridine is basic, so it will form this enolate first, and then let's see. Then we are having treating this enolate with malonaldehyde, this dialdehyde. So it will undergo this enolate will add to this aldehyde carbon, and it will give this beta alpha beta hydroxy compound. Again, similar way, this side is enolate will form, and this will give this beta hydroxy compound. So just write down the next step mechanism. Okay, the next step mechanism, again similarly this enolite will generate in presence of pyridine, and you will get the addition to this aldehyde, you will get this similar way this beta hydroxy compound. So now what will be the next? So next is in pyridine heat, so this carboxylic acid it will remove. So this pyridine will take proton, then this OH bond will break, this will go, and this will fall back, and this hydroxy group elimination will happen. Okay, so in same pot first CO2 elimination followed by dehydration to give this product, this side alpha beta unsaturated product, and downside also same will happen. So downside also to get this here double one you will get an elimination of the C double H and OH will happen. So similar way just write down the mechanism and write down the product. So similar way it will give this product, right? So I guess you have written the mechanism properly. So now we'll see the next problem. Yeah. So this is our next problem. Yeah. This is pretty common problem. So how we can think the CC1 disconnection approach. Yeah, some functional group addition. Okay. So first step is functional group addition. We are adding some ester functionality at alpha carbon here. Then this is pretty simple. This CC1 disconnection. Similar type of reaction mechanism. Okay. Condensation reaction. Okay. Sodium hydride mediated. As I learned, I forgot the name reaction. Anyway, this I also in forward direction. Okay. So now this diester how we could make. So diester basically this we can make via this CN bond disconnection approach between this amine and this methyl ester. Okay, right. So now this we could get via this amine from we nitro from nitro from we get this amine and the rest is same. So this now this nitro derivative. So basically, if you draw these molecules like this CN, this CC, this CC, and this CC1 disconnection, so it will give this three alpha beta unsaturated ester compound. Okay, three equivalents of alpha beta unsaturated ester along with condensation between this nitromethane and three equivalent of this compound will give this product. Okay, not condensation reaction, the normal one for addition product or reaction. So basically, similarly, we took this nitromethane in treatment with DBU, that is catalytic amount, and we are having this three equivalent of this methyl acrylate. So it will give three equivalent addition, one for addition product, like three times one for addition product to this carbon. So you will get this 3 CC1 formation product. Now your next reagent is H2 ranning nickel, right? So what it will do, basically it will reduce your nitro group to amine, and then this cyclization reaction in sodium hydride in presence of catalytic methanol, what will happen? First this CN bond will form, and also this CC1, sorry, this CC1 will also form. Okay, so this CC1 and this CN1 will form in the same condition. First lactam will form, followed by this condensation reaction to give this product. Now you need to remove this ester. Okay, so that you can do some normal decarboxylation, Krebs decarboxylation. First acid formation in presence of aqueous sodium hydroxide. In reflux condition you will get acid, then decarboxylation by using this H plus you will get the decarboxylated product. So this is our target molecule. Okay, yeah, I guess you got it. And if you have any doubt you can ask me, or you can write in comment section. Okay, so if you have any doubt, I'll stop today and I will see you the next class. Till then, have good time and do well. Okay, so we'll stop today. Yeah, and thank you for joining. Okay, so you can leave now. I'll stop.